สวัสดีค่ะสวัสดีทุกท่านนะคะเป็นยังไงบ้างคะได้พักเบรกกันแล้วสดชื่นเลยไหมคะสดชื่นนะคะพร้อมรับข้อมูลต่อไปนะคะในช่วงบ่ายซึ่งเป็นเซสชันที่น่าสนใจมากๆค่ะ Welcome back ladies and gentlemen welcome to the Data Center Knowledge Sharing 2026 Welcome to the afternoon session เดี๋ยวขอเช็คความพร้อมนิดนึงทุกท่านถ้าพร้อมแล้วขอเสียงปรบมือหนึ่งครั้งเลยได้ไหมคะหนึ่งครั้ง Clap your hand once Are you sure that you're ready? Clap your hand once. นั่นแหละ clap your hands. Thank you so much. Welcome everyone. ในลำดับนี้นะคะเราจะเข้าสู่ช่วง panel discussion ค่ะซึ่งก็คือหัวข้อ solving tomorrow's cooling challenges with liquid cooling design นะคะวันนี้เราได้รับเกียรติจากผู้ทรงคุณวุฒิหลากหลายท่านค่ะและในลำดับนี้นะคะใครขอเรียนเชิญนะคะ panelist ของเราบนเวทีค่ะ so without further ado I would like to welcome the panelists to the stage please join me in welcoming Mr. Carl Walker the Mechanical Technical Director from Oregon Consulting Thailand please welcome ขอเสียงปรบมือต้อนรับท่านด้วยนะคะ Now it's a pleasure to welcome on the stage Mr. Mark B from APAC Chief Operating Officer B Global Technology. Dr. Feng Jixie, General Manager of Product Development Center from Hetong Enterprise. And now we are honored to have with us the moderator today, Managing Director South Asia from Uptime Institute. Please welcome Mr. Patrick Chan. Now let us begin the panel discussion. Patrick, the floor is yours. Enjoy.
Good afternoon, ladies and gentlemen. I hope you all had a good lunch. It's sleeping time? No? Okay. So I have with me my friends from the industry. We are going to talk about the challenges in today's liquid cooling. And the way I'm going to do this moderation is very much different from all the moderations, the events that you have ever seen. The role of moderation is basically to share what you have today. It's called data center knowledge, sharing knowledge. So I'm going to also share my part of what I know about liquid cooling together with my colleagues. And what's important is that I have it flash out because I don't speak Thai. And so it's easy for me to put it up there so that you can also see. Also one thing, I will not share the slides. Don't ask me for the slides. I will not share the slides because this is Uptime's IP. Number two, we are going into a process of coming out with an AI course, both in AI fundamentals and AI in ATP. It's coming soon, so be excited about it. Okay, right. So a brief about liquid cooling. As you can see, I put up in the screen. It's becoming the next AI generation. And why liquid cooling? Because it's about high density. The traditional air cooling that you're going to have, the chillers, the DX, they are for enterprise. Hyperscalers are now into liquid cooling. Why? Because you're running about, 50 kilowatt per rack, 60, 80, and guess what? Now you have NVIDIA GPUs. They're going to run on the Vera Rubin of 600 kilowatts per rack, okay? As AI workloads, GPU clusters, I can use this, right? Okay, yeah. As AI workloads are getting on and we are now moving to the traditional cooling into high density data racks with with solutions to address such high densities. So, why does liquid cooling matters? Because it needs to support AI. We talk about AI today. Everyone talks about AI, GPU clusters. We talk about high density, and the current high density is about 40 degrees. Okay, and it reduces basically energy consumption. And we'll come to look at PUE. Enable high rank densities, improve sustainability, and this is a balancing act. So the challenge of this AI that people, yourself and my colleagues here, are basically based on operational risk trade-off. Nothing is generic. So the question now is, what are the benefits of using liquid cooling? The framework of addressing a heat load is a good system design, operation scalability, and economics. So let's start with the first question. The enterprise right now, as you will see, is all the FSI, the telecoms, the IT, and media, everything that we just saw in earlier before lunch. The global data center liquid cooling is estimated about 2.84 B in 2025, and it's going to reach about 21.14 billion by 2032 at a compound rate of 33%. So its expansion, AI is going to go, and high density server racks, liquid cooling, all these are coming. So the question right now, gentlemen, what are the key liquid cooling technologies and configuration used in modern data centers? Let me start with Carl.
Hi, how's it going? Yeah, I guess being a design consultant, the main technology we're probably encountering at the moment is liquid to chip using CDUs. So basically the CDU acts as like a heat exchanger, which transfers the heat from the loop on the CDU side to either the condenser water or the chilled water loop. That's probably the main one that we encounter.
How about you, Mark?
Yeah, I have to agree with Carl here. I think 99% of the data centers that we are doing now is direct to chip cooling. So it has taken the market. A few years ago, everyone was talking immersion will take the market, but we are not there yet. We're also collaborating with OCP, the Open Compute Project, right? That's founded by Microsoft, all the big guys. And in that forum, they are discussing a lot of our immersion coming next. But what we see in our day-to-day work is direct to chip with the CDU, as Carl explained. Yeah.
Okay. To you, sir. Doctor.
Yeah, I think for me, we have the same appointment with those two guys, those two gentlemen. Right now, I think, of course, liquid cooling direct to chip is the only solution. I cannot say only solution, but it's it already be used in most technology at this moment. But what we think or what we observe in Taiwan is that right now they are not talking about not only liquid cooling direct to chip, but we also put more attention on the two-phase cooling at this moment. But how about the emerging cooling in Taiwan? Because due to the maintenance issues, so in Taiwan I don't see a lot of partner in this area. But we have found that in China, a lot of players about the AIDC, they put a lot of intention in the emerging cooling. So it is what I observe in Taiwan.
Thank you. Okay. Now, let me ask the audience, how many of you basically have installed liquid cooling? Just put up your hands. No. Right? How many of you actually have installed liquid cooling in your data centers? Just put up your hands. So now, okay. Let me ask you another question. Do you know how many types of liquid cooling are there in the industry? Anyone? This is it. There are about 10 types of liquid coolings out there. From direct to chip cooling, immersion cooling, single phase, immersion cooling, two phase, cold plate cooling, rear door heat exchanger, in-row cooling, overhead manifold distribution systems, hybrid liquid cooling, chill water, advanced hybrid cooling. That's that many. So I've also done my part of being part of a moderator slash panelist. I've done some research, and I have, just for information, all this have been vetted by our uptime intelligence and our subject matter expert in AI. So, next question. It's no longer simply how to cool servers, but how to design an integrated thermal, electrical, mechanical operational ecosystem that remain efficient, reliable, scalable, and sustainable. Because liquid cooling, you do not basically employ day one. You do not know. Right now, you may put in, say, 300 megawatt of data center day one. But you do not know what is going to be day two. It's going to be 600. With Vera Rubin coming in and all that, you're going to be 600. So there are going to be challenges, right? So over to you now. I'm going to go this way now. Doctor, what are the challenges?
In terms of the challenge, because just like you mentioned or you see in the slide, how to do the integration between to consider about to think about the thermal, electrical, and mechanical. What we think is that I think at this moment the challenge is not to cool the server itself, but we think is how to optimize to balancing all the environment, all the elements here, even thermal efficiency, power consumptions. What we do or what we propose is that what we think at this moment is we don't want to keep more attention on the optimization problem. What we put more attention is how to manage the development process, how to think about the when we during the development process, how to manage to optimize all the design. So based on our approaches, we propose we adapt a V model. Actually, it is from automotive process, and during this process, it is start with the system requirement in the beginning, and then during the requirement analysis, we need to think about how to do the optimization between these matches. So it is what we think. So the key challenge is not to cooling down and also not to do the optimization because we have a lot of technology here, and the problem is how to manage all during the development process, start from requirement and then design deploymentation, and finally make the testing. So the key point is how to manage all the development process.
Thank you. Do you, Mark?
Yeah. The key challenges that we face, like being viewed from the designer of the data center, first is understanding the operator requirements, right? Because nowadays the operators, the first thing they say is, I want liquid cooling. But then as designer, we need to ask why, right? Because some data centers, liquid cooling is not for all the data centers, right? It's for most of the data centers being built right now, that is all the AI data centers. But there are still a lot of data centers being built for the cloud, being built in the edge, like near the customers. And all these maybe will not need all these GPUs, will need other type of loads, right? So the first challenge for us is understand if the client really needs this liquid cooling. Yeah, and
I think probably a challenge for us is often we might design co-location data centers, so we don't necessarily know what the end customer requirements are. So I guess making sure that we've got a design that's flexible, because we don't know if the liquid to air ratio is 60-40, 80-20, or the temperatures of the incoming water to the CDU might vary. So we probably try and pick the worst case, and then that way you can wind it back if you need to. But probably having a design that is flexible, because there are many different types of liquid cooling that can accommodate those changes without having to make substantial retrofits and stuff to the building.
Thank you. Now, there are no right or wrong answers. It's just about inputs. This is data center knowledge sharing. So I'm going to share with you my inputs, my research, what are the challenges in the industry? Number one, water usage and sustainability. Okay, critical basically concerns about water scarcity. I think this morning they got this company called Suntech, what, right? Talk about water cooling and how they're able to address the problems. Then tower evaporation losses, regional environmental regulations. In the US, they're basically very concerned about hyperscaler data centers that are using a lot of not just power but water. Treatment requirements. I think you saw that earlier on, the corrosions, right, and the biofueling risks. The industry is moving forward to new technologies, new way to address this, okay? I'm not going to read out all that. Reliability and leak prevention. This is one of the most challenging. I have videos that show people or data center operators having challenges in leakage, okay? Where the liquid just bursts out, okay? The thermal control complexity is another challenge, the rapid thermal spikes. And why is that? Because it creates harmonics in your data centers. And when you run chillers, it locks your chillers. And that's why you have cases that. So be careful when you're running a GPUs. You have to make sure that you have all the given check and balances to address harmonics. And these are the things that create challenges. Infrastructure retrofit constraints. This is again, there's a limitation there, the pipings. You can't do retrofit in a 10-year-old data centers that wants to go into AI and liquid cooling. You can't. You have to build new ones. So if you are doing, say, a floor that is first floor, and you're going to have a second floor doing AI, whether I'm AI ready, you got to take into consideration that as your strategy. Gaps. You got to look at the gaps where, whether you have vendors, you have inconsistent CDU interfaces, you got to look at all that. Your heat reuse economics, you got to ensure your PUE, how you're going to address those, your cooling convergence, and so skill and operational readiness. And this is the part I think, Carl, you were talking about. Are your people ready? Are your people knowledgeable to have attended any AI course operation, know how to operate this, okay? So these are examples, and now we come to the third question. I hope those helps. I hope those helps, all those, tell me if it helps. Put up your hand if you think it helps. It doesn't help, then I'll just let you say bye-bye. It helps, right? Okay. Traditional facility teams may not have these competencies at scale. Training and operation maturity are now a strategic issues. If today someone wants to build AI factory, it's a common term. Are your team, are your people ready for it? So what are the emerging future directions, trends that are shaping tomorrow's schooling? Over to you, Carl.
Look, I'm probably not so sure about the facilities teams, but I guess one of our biggest challenges as a company, the data center sort of market has grown very quickly in a very short space of time. So so I guess the skills and the knowledge is probably still growing. And I guess the challenge for us is simply getting enough engineers, and often we sort of end up taking more junior engineers and training them up, but then we have to try and keep them as well, and they don't get pinched by clients and other consultants. So yeah, it's probably from our perspective.
Mark, your team ready for this?
So yeah, from myself, I think I can explain a story behind this maybe, because we were meeting NVIDIA last week, right? So NVIDIA was complaining about the consultants, about the industry, saying, I have the racks ready to work at 40 degrees, even 45 degrees. You can put the water into the rack, but you, all designers, still rely on chillers. You don't use free cooling. So I think as a designer and all the industry, we really need to push for this high temperature, using dry coolers, that we don't use power, either water, right? So that's something that the future, I'm sure, will push for PUE improvement, for less water consumption. So the designing team, we need to to also push for this.
Thank you. For your information, Mark have not seen these questions. We had a call, I think only Carl and Doctor have seen these questions, okay? Mark have not seen it, but he's able to answer this from his experience. It show how experienced he is, now you know, okay? So B Global Tech is one of the very experienced company. Okay, you here, buy me coffee. And over to you, Doctor.
In terms of emergency feature duration, of course, power, thermal load, water load is the most important things because we need to provide more we need to improve thermal efficiency and also thinking about the power efficiency. So first thing, we would need to start with the power load of each solution. And then another point of view is that right now, because in the data center, we need to integrate all the different fields like chemistry and electrical, mechanical. So we need to have a team. They have a system integration technologies and all of the knowledge within the team to deal with all the problems, not only for the cooling, but also for the electrical, mechanical, even control and maintenance.
Okay, comes to my slides. If you want to look at training, you want to address tomorrow's trend. We have a counter, basically, my colleague said, see, Matt is writing all the questions. Talk to Matt, talk to Parag. They are the ones that basically will address your concerns about tomorrow's trend. So basically, the emergent future directions right now is basically is about temperature. It's all about temperature, and it's getting higher and higher. That need to reduce, and they have to be, whether they are going to be chiller dependence to improve, is a technology that people are working on. There's this one data center in Australia, I won't mention the name. They're going to do away with liquid cooling, and they're going to use hybrid cooling to address this, okay? It's the R&D. And another way is to basically address the two-phase cooling and what you see here. Future processors are designed basically to build around the architecture. And basically, it's about chip level thermal critical. So in practice, for any design, good design, you got to look at it in the long term, how to eventually address in the increasing of the chip. The next challenge basically is about operational simplicity. The more complex you have in your data center to address any high density is going to be a disaster. Okay, you got to look at the economy. You got to look at your TCOs, and basically you can look at standardization, because your first floor of your data center AI using liquid cooling will be different from your second floor in 2 or 3 years' time. Technology changes. Okay, the winner of this, in terms of when you're doing RFP, when you're doing all this interviewing, the winners for data center operators and vendors that treat liquid cooling will be basically, it's not an add-on. It's not like the old, you just add on, you have in-row cooling and all that. No, but basically how you integrate your platform into a very tight AI computer architecture. Okay, you see all this vendor out there, you see that. Try and look at it is, firstly, how do you add on to modular? Can you create modular liquid cooling? So next question is the industry that's really tend to be structured and difficult to avoid. Example, data centers, infrastructure's reality is that the industry is no longer whether liquid cooling works, but it's about compute density is rising faster than traditional cooling efficiency. Give you an example. We are talking about right now, a high density rack is about like 50 kilowatt per rack. And I can tell you in probably 6 months' time or more, you're going to run at 600 kilowatt per rack. And Vera Rubin is the one, whether you like it or not, is coming. So what are the real challenges in addressing this? Doctor?
The real challenge in the data center is, I think, is the timeline mismatch, because the GPU update rate is very quickly, like about 12 months. But if we are talking about building the facility of the data center, it takes like 2 years, or even we use like a containers design, it takes 1 year. So the problem is like if we don't do some like a speed to market approach to deal with the mismatch timeline, it would be some problem, because if we buy, at this moment we buy a GPU, but we take like 2 years to build a facility or to build an AI data center, which means your GPU is out of the date. Even you open the data center, you put on the data center. So the problem is how to speed up to market. So in our point of view is that we propose, of course, a lot of people mention about the modular prefabricated design. It is due to one to standardize and to prefabricate it to build the data center in advance, and then we will have like we only need to spend like 6 months or 7 months days to deployment the data center. So it is what we propose.
Thank you. No?
Yeah, I agree with Dr. Feng. So one of the key challenges now is the speed to market. The GPUs get ready from NVIDIA and they can send it to your site in 6 months, but you need like 2 years to design and build the facility. And what happens a lot of times is what you have designed 2 years before, when the data center is ready, you need to adapt it to the reality that the GPU needs, right? So if you design a data center 2 years ago for 20 kilowatt per rack, now the GPU comes and needs 200 kilowatts per rack, right? So make sure that you design flexibly enough your data center for what's to come in the next couple of years.
I guess from my perspective, probably one of the key challenges is maybe not so much the compute density, but just the IT load of the data centers is just growing exponentially. So might have been 30, 40 megawatt data centers were pretty standard a couple of years ago. Now 150 megawatts is pretty standard. I know of data centers in Australia where they're talking about 500 megawatts. So I guess the challenge that I think is there is just the capacity of the electrical and water networks to support that sort of water and electricity demand. And I think in Singapore there was a memorandum of no data centers for a while there because they were just running out, the networks are running out of capacity. And I guess we've had a bit of it just from Oricon. We've noticed in Indonesia, Singapore, there's a bit of a wave. So Indonesia will have a whole lot of data centers, Malaysia will have a whole lot, Singapore, and I think it's Thailand's turn at the moment.
Thanks, Scott. Okay, here's my research paper in the next slide. So how do we address these challenges? Okay, it's no longer how to cool servers, but how to design. But by the way, these slides are not given, so you can take notes. How to integrate thermal, electrical, mechanical, and operational ecosystems that remains efficient, reliable, and scalable, sustainable. Today, it may not hit you, but your client, investors are coming and asking for 300 megawatt data centers available or not. Malaysia is already running out of all data center space. We have cases where they come to me and says, do you have 200 megawatt data centers? I'll sign the PO. That's the fact of life. We have actually searched and we found one in Bangkok who can address that. I'm not going to say who. And basically, the condition is must be liquid cooling. That's the condition. No chiller, no air cool, no DX, must be liquid cooling. So the problem is how do we cool a server? It's now how do we engineer a stable AI compute ecosystem across chips, racks, hydraulic plant, etc. The shift is why liquid cooling is becoming systems engineering rather than a facility add-on. So These are actually examples. How do we address this? Modern AI accelerators create high average heat loads. A single GPU may exceed 1,000 watts to 5,000 watts, okay, with localized high spots. The challenge basically of these is able to remove heat across the die, the ensuring the heat is extracted evenly, okay, across the die, ensuring the heat is basically evenly from all regions, preventing hotspots. This basically becomes harder when transistor density increases, when high bandwidth increases, and chiplets even create more uneven thermal maps. Also, liquid cooling introduces flow balancing, pressure management. So the challenge is the flow starvation. How do you ensure the pressure is consistent? GPUs may exceed 1,000, but they also create overheating. Okay. Now, the other issues, challenges are temperature cycles. Okay, and they are basically it's about pump out, soda fatigue, PCB bending, and then especially problematic in large AI GPUs. So the power density standards are the one that basically they were designed 5 to 15 years ago, but now they're moving towards 150 racks. So how do you address those? It's about delivery power, flow loading. Have you noticed that the flow loading, what I see, I'm not sure whether you all agree, we used to have race flows. When you have high rack densities, race flow may not become relevant anymore. The flow loading that anyone that they're running now is basically about 12.5 kilonewtons per meter square. With AI coming in, it's average about 40 plus kilonewtons in the flow loading. So how can race flow able to sustain that weight? Okay, so here we have also climate, water availability and climate. You heard about that. We have climate change where temperature creates a havoc to the data centers like drought risk, water scarcity. You heard of El Nino. It's coming and it's going to hit big time. And basically, it's about how facilities should reconsider using water reuse. Now, the cooling of AI, you cannot simply use any water. Yes, you heard about using recycled sewage. It has to be treated to be potable water, okay? So you have energy efficiency versus reliability trade-off, and it's about understanding PUE, WE, uptime reliability, operation costs. Interdependency between chip and facility design. The challenge is basically affecting your hydraulics, your racks design, and the cooling topology. So complexity in terms of operation. You basically need to someone who have a hybrid expertise. The trend, what we see right now is not just pure liquid cooling. They are in the uptime intelligence have actually introduced what people are using now called hybrid cooling. So scalability and future proofing. Remember the facility, every data center is about 15 to 20 years life cycle. Okay, and AI evolves every 18 to 36 months. The AI that you learn today, the AI that you learn the certification, don't be too excited about it. You say, oh, I'm an AI certified. 3 months later, it's no longer valid. AI evolves very fast, unlike in the engineering days. Okay, so these are basically how do you address modularity? Okay, so still a few like in terms of pressure, how do you do low carbon cooling, renewable integration? Okay, so the next question is the data center cooling dilemma. Air versus liquid. I'm sure all of you have gone through this, air versus liquid. facilities will likely deploy liquid cooling loops, especially for the AI GPU. You can see down there, they actually have some that they do loop, all the loops, maintain traditional air cooling for standard network and storage racks. So are you seeing more of these hybrid designs in your current facility planning? Or is the organization going out for all out for liquid and new builds?
From my point of view, I think hybrid design is definitely be the solution, because like in the data center, we don't have we will have like a rack, server rack, not only server rack, but also we will have storage rack and management rack. If we were talking about the server rack, definitely if we are using a GB300, of course, liquid cooling. But if we are talking about the storage rack or management rack, definitely I think air cooling is good enough. So I think we need both air cooled and liquid cooled in the same region for the data center.
Yeah. Agree. All the facilities needs to be hybrid designs. We are full. All our designs is hybrid always. The liquid cooling is gaining more part and more part. Now hitting 90% of the facility, 95%. But we still need this cooling for the room, for the storage, for network racks. So all these still need to have the traditional cooling to the room, right? So designs have become more complex, right? Because it's not that you change to liquid cooling, you forgot about the whole design. You need to have liquid cooling and air cooling both ready for your data center.
Cool.
Yeah, as Mark says, I think a lot of ours are hybrid. I guess for a lot of our projects, I mean, the maximum electrical load is sort of dictated by your connection to the grid. And I guess what we try and do is make sure you have the flexibility. So at the end of the day, if you have liquid cooling, it means you can have more IT load because you've got less mechanical load to be catered for. So we try and have that flexibility a little bit of air cooled and liquid cooled at the moment.
Thank you. I've seen one hybrid design liquid cooling in effect in Malaysia. There's one data center, it's running about 20 megawatt. They're running hybrid. They're not purely liquid, but hybrid, air and liquid. So this is what you see between in terms of air versus liquid. The data center this is the dilemma. Do I use air? Do I use liquid? For many, many years, keeping data center cool rely on simple premise. So, you have racks now pushing beyond 40 kilowatts. How do you support that? So you're mapping out a data center infrastructure, understanding the tipping point between air and liquid. So it's a balancing game. You cannot put too much on air or too much on liquid. Okay. So the established standards. This is not uptime standard, but this is a research paper standards, okay? There are pros and cons, okay? It's basically based on it's cheaper to install a universal, basically easy to maintain type of cooling. But the con side of it is that the challenge side is that air is a terrible conductor of heat. Okay, pushing enough of air, you will end up basically running the fans to try and cool it, making it harder. So the best is actually meant for legacy enterprise loads that standard cloud deployments between 20 and 30, you can use basically air cooling. But for liquid cooling, it's a different game. It's 3,000 times more effective and transferring heat and air. So the pros side is that it boasts of thermal capacity, whether through direct to chip or full immersion. What happened? I think the press. Okay. Right. So, and the pro side is that basically with all this direct cooling, it's a PUE. Do not disregard the importance of PUE. Banks or financial institutions that lend money to build data centers will basically insist on PUE. And basically they insist, and you basically those who are actually able to, address the PUE issues, they actually apply for green bonds. In Malaysia and Singapore, the authorities or regulators are now pushing towards standardized PUE of 1.3 and below. So the challenge is that you have to look at the complete architecture shift. So you're going to look at the CapEx versus the OpEx, and it's only best for basically you're running on high density data centers. So the next question, should liquid cooling design apply to redundancy or resiliency? Does resiliency matter more in liquid cooling or just redundancy? We talk about today about redundancy is not equal to resiliency. So should liquid cooling be designed to address this resiliency or redundancy? Okay, your turn. Oh, Carl, your turn. Sorry, I lost.
Yeah, look, I guess both are still important in a liquid cooled design. I guess, and again, we're probably looking at it from the designer. We probably tend to sort of design up until the CDU, and then what happens on the CDU side, all the interesting stuff is by someone else. So we probably don't have, yeah, as I say, so we're probably more on the liquid cooler, on the water side of it. But yeah, that's probably all I've got to say.
Yeah, from my side, I think one complexity that adds on the design is, as what Carl was mentioning, right? From the CDU to the rack, is no longer a simple design that is just connecting, right? You need a proper design specialized for the rack that you're receiving that may include thermal storage tanks inside the data center to be able to manage the spikes on the load, right? So apart from the typical redundancy and resiliency that you have on the cooling system, now you have to add a new design also on the secondary loop that is like a new package for designers, right? So the typical base building, you design until the CDU, until the PDU, but now we have to add this design until the rack level, because not every data center will be the same, right? Depending on the type of GPU you get, you will need different connections to each of the racks. So it's one added design and redundancy and resiliency that we need to add to the designers.
How about you, sir?
I think for the target of both the redundancy and resiliency, the target of those two items is to how to keep your data center continuously operation. So both are very important. But if I am the technical, I would like to say that I love redundancy because that's quite easy. We just buy another component and put it into the data center. That's quite easy. But if I love to do some research on the liability or robustness, I would like to say that resilience is very funny because we need to put more attention or more detailed research regarding how to improve the reliability of the system.
How many, now I'm going to ask the audience, how many of you believe that you're happy with redundancy design? Put up your hands. No? How about resiliency design? No? Why is this question important? Redundancy versus resiliency. A few months back in Middle East, in Dubai, AWS went down. It was down. And it was not because it was hit with any explosion. It was because the drones, the drones that was exploded, the debris hit AWS data center. What was the cause of that down? It's because it was designed to redundancy and not designed to resiliency. Now you understand the logic, okay? So, should liquid cooling apply to redundancy or resiliency? So basically prioritizing resiliency is very important than redundancy. If you're an investor here, any of you are investor, or any of you are data center owners and operators, and you have designers that come to you and say, no problem, redundancy is okay, you don't need to do resiliency, you will find out in 5 years' time. Because redundancy, as what our friends here says, right? It's easy. Buy 2N, not N plus R. 2N. If one costs 100 million, times 2. Simple, mirroring each other. Your total cost of ownership is going to kill you after 5 years. It's going to basically deplete your ROI. Resiliency is not redundancy. It's N plus R, where you have 3 plus 1 or 4 plus 2. It all depends on experience engineering. So it works well for components failures, redundancy. But the challenge is your liquid cooling. Liquid cooling is expensive. Try looking at the liquid cooling. If someone out there have a deep, look at it. Ask yourself, what if the pipes leak? There's a flow, there's leakage in pipe. How do you transfer that data, that liquid cooling to the next redundancy or next secondary equipment to support the server? Why do you need liquid cooling? Because the server is so hot, like 40 kilowatts, so high density, that if that is like 1-to-1, you need to have 2-to-1. And if that one is down, before you can mention your name, especially in Thai, you have quite a long name, you can mention, it will go down. It will be just fry up itself. So examples basically that can cause disruptions are load segmentation, isolation views, leak detection systems. Those are the ones that basically can cause disruption. So why is it still necessary? Because you need to basically address your primary pumps, you control your PLC systems, your power to cooling equipment. So think of N plus 1, not 2N. Okay. So what is the design philosophy to a good liquid cooling design? Redundancy versus resiliency. I think it's quite. You all know the answer already, right? So let me hear from you.
Yeah, we already answered the question. The philosophy for me is quite easy. Just keep the AIDC continuous operation. So both are very important, and redundancy is very expensive, but we love resilience because liability, it guarantees that the AIDC can always help you to earn some money. Thank you.
For me, let me add on this redundancy versus resiliency, that you can have a very redundant design, but if you don't have the proper product, right? If you have N plus 1 gensets, but your gensets doesn't start up, are failing every few days, then you don't have resiliency, right? You have N plus 1 gensets, but the gensets are always down, right? So it's about the designers, but also on the vendors' works to ensure that the resiliency is in the data center.
Carl.
Yeah, I mean, I think with the resiliency, I guess trying to just limit if a component does fail, just limiting it to that area and still maintaining that the rest of the data center can operate. So yeah, something like a loop in your process water side, so that if a CDU fails, you can just isolate that one section.
Thanks. So do you agree that a good cooling design should be resiliency? Put up your hands. Okay, good. At least got some hands. The other believe redundancy. If you want to go redundancy, it's your money because you got deep pockets. You do. It's simple, but do not get into a trap where consultants or designers says 2N is better than N plus 1. So this is my answer. Okay. What is important is that you have to ask the questions when you do the design of cooling, redundancy versus resiliency. What can fail? Can that failure be isolated? Can the system continue operating if there is a leakage, if there's a blowout? How can it quickly recover? How do you isolate leaks without taking downward loads? And what should the failover be? Unfortunately, I did put a video here. I should show you a video, but because of time factor, I didn't want to show you a video. It's a true case that we have on this issue about redundancy versus resiliency. So the framework basically is about resiliency driven. It has to be rely basically heavily on resiliency than redundancy. Okay, so there seems to be a lot of deployment companies like Vertiv, Schneider Electric, NVIDIA, and Supermicro as rack densities keep rising. I'm letting you know that you cannot run away from AI. AI is coming. And of course, people say, oh, AI create jobs. It also deplete jobs. It also take away jobs. But AI is coming because we are now moving into a next evolution. It's not industrial. It's not digital. It's information revolution. People want information fast, right? So you have people using all form of inferencing tools to basically get information. The last question. Hope you're still awake, huh? All put our hands, you're still awake. Water strategy. I think someone basically from the earlier on talked about water. It's often underestimated. What are the challenges of data centers and or AI operators will encounter? And before we answer that question, we got this question actually from one data center operator, we all forgot about water. We look at power, but we forgot about water. And I echo the same statement that was addressed earlier. So, over to you.
Yeah, I think, as I said, so I guess as people, the data centers will usually have a two-end electrical connection. They want it from two different substations. But yeah, the water, I mean, we've sort of realized like in Thailand, you can't necessarily get the same level of infrastructure because you'll have the dam, it pumps the water to here. So you still have that pump station as a single point of failure. So it is something that needs to be considered, and you might have to offset that with additional water storage on the site. And I guess the other thing is probably just the amount of water that the data centers use. I worked on a project in Adelaide where we were actually the client paid a lot of money to get a recycled water connection. So they basically use the treated sewage goes to a sewage treatment plant, and then they're using that water, which was considerably cheaper than sort of the traditional town's main connection.
Yeah, from my side, I see the challenge on water. First is that you don't know in the future if you will be able to use the water, right? In some countries, happen that you design your data center that consumes water, and then the government changed the rules, and in 5 years, data centers are forbidden to use water, right? So if you want to keep your risk down, try to design waterless designs with no water consumption, then you lower your risk a lot. Yeah.
Doctor?
Oh, sorry. For the operator, the challenge of the water strategy is, I think the challenge is that how to make a balancing or decision about the PUE and WUE. If we want to lower the water usage, we need to increase the PUE. But if we want to reduce the PUE, of course we need to increase the water. So another thing we need to think about is that in the future, probably the environmental may be changed. So water probably may be even the city pipe is broken, or we don't have no longer enough water. So it will be some difficult to make a decision about how to design the AI dish, even to choose one great place for the AI data center.
Okay, thank you. Now, we talk about water strategy. Water will always be a challenge. There are many solutions to it. Some use water treatment plant, their own water treatment plant. Some are basically like in Singapore, they're looking at district cooling. There will be many people looking at ways of addressing water shortage. El Nino is there and it's coming big time. So these are the challenges, and how do we address this? We often underestimate the water quality standards. How do we manage corrosion risks? basically what happens in the water stressed regions like Middle East. We have one 400 megawatt data center called the Hexagon, not the Pentagon, the Hexagon data center in the Middle East. Where you think you're going to get the water from? Then you have warm water cooling, leak containment. Those are actual facts that's happening right now. And the strategy is basically in traditional data centers, we all talk about power. But ladies and gentlemen, we are moving away from that. Power can be addressed. Water is another challenge. Okay, so many operators basically are focused on megawatt capacity and long-term water stability. How long can water last? Okay, that's a question you have to ask. And basically, hyperscale campus, water is no longer just a utility input. It looks at thermal, it basically becomes a thermal transport medium, addresses the thermal, becomes an operational risk factor, climate, ESG, and geopolitical resource issues. So this is why you have the AI water equation. Look at this chart, basically. These are where it's going to move from 5 to 15 to 300 to 500, as where we were talking about earlier on, the Vera Rubin. Then you will see when density rise, air cooling efficiency collapse, liquid cooling adoption accelerates, and heat rejection demand increases. And basically, that's all? Okay. Basically, it's not the end of the world. Sorry, I pressed wrong button. Sorry. Is it because I'm over time? No?
no
Okay.
ขอสไลด์ของท่านกลับ
What I'm saying, sorry, I have to go back. It's not the end of the world. A good engineer, because right now, people tend to overblown the issues. And I asked earlier on, how many of you actually have implement liquid cooling? I'm not sure many, maybe you all have, but you all don't want to say. Seek advisory, advice, guidance, expertise from the experts, okay? I'm not here to sell Uptime, but I would like to, but Uptime basically has services that looks at AI design from planning, testing, commissioning, to basically encompasses both power and cooling. So we have our colleagues in the booth to basically drop by. We actually have that service to give you basically at our advice. Okay. With that, ladies and gentlemen, thank you, sir, all of you for attending. I congratulate you for keeping your eyes still open. This is a very technical subject, which I find myself even struggling. Okay. So with that, thank you.
Thank you so much. Please give a big hand to our panelists and also our moderator. Thank you. ขอบพระคุณค่ะ และนี่คือ panel discussion นะคะ อีกหนึ่งช่วงนะคะที่ได้ผ่านไปแล้วค่ะ solving tomorrow's cooling challenges with liquid cooling design นะคะ เดี๋ยวขออนุญาตถ่ายภาพสักครู่เดียวนะคะอย่างที่โมเดอเรเตอร์ของเราได้บอกไปค่ะถือว่าเป็นหัวข้อที่ค่อนข้างเทคนิคอลแล้วก็ค่อนข้างยากมากแต่ว่าเชื่อว่าทุกท่านนะคะจะเข้าใจกันได้เป็นอย่างดี Thank you so much Thank you very much for the valuable insights